Some say it's just a comet, a ball of ice and dust behaving a little stranger than usual. Others look further, suggesting it might even be an alien vessel of some kind. But there's a third possibility, one that's grounded in real science, that objects like 3I/Atlas could act as planet starters. By carrying raw material across interstellar space, they might help jumpstart the growth of gas giants like Jupiter, speeding up the slow process of particles sticking together and forming new worlds. If 3I/Atlas proves to carry alien material, it could rewrite our understanding of how worlds like ours are born. But what evidence backs up this radical idea? And what secrets are still hidden behind its glowing veil? For decades, astronomers believed the path from dust to planet was a simple matter of sticking together, tiny grains in a young star's disk, colliding and clumping until a world was born. But the reality is far messier. Laboratory impact experiments and computer models reveal a stubborn barrier. When particles grow beyond a few centimeters, collisions often do more harm than good. Instead of merging, these boulders bounce off each other or shatter into fragments. This is the so-called bouncing barrier, and it's a major headache for planet formation theory. Even in the weightless, gas-rich environment around a newborn star, meter-sized rocks slam together at speeds that make glue useless. Most attempts to bridge this gap end in breakup, not growth. Some researchers have tried to patch the problem with ideas like sticky ice coatings or by invoking turbulence to help pebbles pile up. But none of these fixes fully explain how planets form so quickly and efficiently. The numbers just don't add up. Simulations stall out, and observations of young disks show planets appearing faster than current models predict. So the question hangs in the air. If ordinary collisions can't get us from dust to planetesimal, what's missing from the story? The answer may lie far beyond our own solar system, carried in by cosmic wanderers that don't play by local rules. Susanne Pfalzner, a planetary scientist known for challenging the status quo, stepped into the spotlight with a radical proposal. At the Europlanet Science Congress in September 2025, she argued that the missing ingredient in planet formation might come from far beyond the local neighborhood: interstellar objects acting as cosmic anchors. Her idea: when a foreign body like 3I/Atlas plunges into a young gas-rich disk around a newborn star, it doesn't just pass through. Instead, it becomes a seed, a nucleus large enough for dust, gas, and pebbles to stick to it, bypassing the notorious bouncing barrier that stalls homegrown rocks. In simulations, these seeds act as gravitational magnets, collecting material far more efficiently than random collisions alone could ever achieve. The process is surprisingly efficient. A single interstellar object, once captured by disk gas drag or slowed by a lucky encounter, can snowball into a planetesimal, then a protoplanet, in a fraction of the time traditional models require. Pfalzner's anchor model suggests that these cosmic immigrants could explain why some planetary systems form giant planets so quickly, and why exoplanet diversity is so high. But the road to this idea wasn't easy. She faced resistance from peers and grant agencies, with some dismissing the seed hypothesis as unnecessary or unproven. Yet, the upcoming close pass of 3I/Atlas gave her theory new urgency, helping her secure a rare plenary session at Europlanet. There, she laid out the anchor concept. Not every planet needs a foreign seed, but when one arrives, it can jumpstart the entire process. For researchers watching 3I/Atlas now, the theory offers a bold new lens. Maybe the universe is littered with worlds that began as cosmic trespassers. Astronomers used to think interstellar objects were cosmic rarities, one-off wanderers like Oumuamua or Borisov, slipping through the solar system every few decades or centuries. But new surveys and simulations have upended that view. The numbers now suggest a galaxy swarming with these travelers. For every object we spot, billions more may pass unseen, too faint or too fast for our telescopes to catch. Studies from the Vera Rubin Observatory and Atlas survey estimate that at any given moment there are hundreds of thousands of interstellar objects larger than 100 meters crossing the outer solar system. And that's just in our neighborhood. Scale this up to the entire Milky Way, and the picture changes completely. Trillions of such seeds drifting between the stars, each carrying the potential to spark new worlds. Computer models show that when a young star forms in a dense cluster, its protoplanetary disk doesn't exist in isolation. Instead, it's bombarded by a steady rain of foreign rocks, icy fragments, and ancient debris, remnants ejected from the birth pangs of other planetary systems. The odds of capture rise dramatically in these crowded nurseries. Gas drag and gravitational encounters make it surprisingly easy for a passing interstellar object to lose speed and settle into orbit around a new sun. In some simulations, millions of these seeds are swept up by a single disk during its brief planet-forming years. This constant exchange of material isn't just a theoretical curiosity. It may help explain why exoplanet systems are so wildly diverse, and why some worlds, perhaps even our own, bear chemical fingerprints from far-off stars. If planet formation is a galactic relay with building blocks traded across light years, then interstellar objects like 3I Atlas aren't outliers. They're messengers of a universe where every world is, in some sense, an adopted child. 3I/Atlas is no ordinary comet. First flagged by the Atlas survey on July 1, 2025, it streaked into view near Jupiter's orbit, moving at nearly 60 kilometers per second, far too fast to be native to our solar system. Its path is hyperbolic, a one-way ticket from another star. But it's the chemistry that truly sets it apart. Spectroscopic data from Hubble, JWST, and VLT reveal that 3I/Atlas is loaded with carbon dioxide, far more than any local comet. Water ice is there, but in smaller amounts, and the usual signatures of diatomic carbon and cyanide are present, though at lower levels than expected. Atomic nickel vapor, rarely seen in solar system comets, stands out in its spectrum. There's barely a trace of ammonia or ethane. Even the dust, rich in organics and with a deep red slope, resembles D-type asteroids from the frigid outer reaches of planetary systems. Every measurement points to an object shaped by alien conditions, forged in a cold, distant birthplace. Its volatile inventory reads like a chemical passport from another world. Not everyone is convinced that cosmic seeds are essential to building planets. Many planetary scientists point to pebble accretion, where small, centimeter-sized stones drift inward and merge with larger bodies, as a process that can bypass the bouncing barrier without any need for foreign objects. Anders Johansson's group, for example, has shown that in the right conditions, streaming instabilities can clump pebbles together rapidly, forming planetesimals in just a few thousand years. Other researchers favor the idea that disks can pick up material directly from passing molecular clouds, or that close stellar encounters can deliver rogue planetesimals from neighboring systems. Some critics argue that interstellar objects like 3I/Atlas are just too rare to play a major role, with only 3 confirmed so far. Funding agencies remain divided. Some push for more sky surveys to find these wanderers, while others question whether precious resources should go toward chasing what might be statistical flukes. The debate is fierce, with each camp defending their models and priorities. As 3I/Atlas approaches its close pass by Mars, the stakes for proving or disproving the seed theory have never been higher. September 12th brought the first real surprise, an outburst from 3I/Atlas that sent its coma swelling far beyond predictions. Astronomers scrambled to secure every possible telescope slot, from the Hubble and JWST down to backyard setups. The rush wasn't just about curiosity. October 3rd loomed on the calendar, a close flyby of Mars, with orbiters and surface landers all primed to catch the interstellar visitor at its brightest. Teams coordinated rapid-fire observations, each hoping to pin down the comet's volatile inventory and dust structure before it slipped from view. As the month ticked by, the stakes only grew. The perihelion, or closest approach to the Sun, would come in late October, right as 3. I/Atlas skirted the limit of solar glare, threatening to vanish behind the Sun's blinding light. Even after that, a final rendezvous with Jupiter in mid-November promised new gravitational twists and perhaps another outburst. For planetary scientists, these weeks became a global relay. Data handoffs from one observatory to the next, every minute precious, every spectrum a potential clue to how alien seeds might spark new worlds. On July 1st, 2025, astronomers recorded the third confirmed interstellar object, 3I/Atlas, entering our solar system on a hyperbolic path, clear proof that material from beyond our Sun still arrives today. Unlike local comets, 3I/Atlas shows a strong carbon dioxide signature and a lack of typical solar system molecules, confirming its foreign origin in documented spectra. Research led by Susanne Pfalzner proposes that such objects could act as planetary seeds, anchoring dust and accelerating planet formation. Billions of similar bodies are estimated to drift between stars, yet the frequency of their encounters with young systems and their true role in building planets remain open questions. As 3I/Atlas makes its close pass by Mars this October, every new measurement will test these ideas against direct evidence. The discovery of 3I/Atlas demonstrates that cosmic exchange is ongoing, and the building blocks of planets may be far less isolated than once believed.